This morning we heard a lot about the hostile environments that explain why we want to build space habitats, and we heard about the materials that we're going to use for those, but we haven't heard much about the actual structures that we would like to build in space, and this is exactly where we have the next speaker here. Dr. Scott Howe is a licensed architect and a robotics engineer at NASA's Jet Propulsion Labs right here in La Cañada. He earned 2 PhDs, one in industrial manufacturing engineering from Hong Kong University, another one in architecture from University of Michigan, so that's a perfect qualification to talk about space architectures. He spent about 13 years of practice in Japan, 6 years at Hong Kong University, and he specializes in robotic construction and is also on the NASA development team designing deep space human habitats and outposts for the Moon and Mars. We're delighted to have Dr. Scott Howe with us, and he's going to talk about space architecture.
Let's give him a warm welcome.
Okay, it's great to be here, and it's great to get a lot of the folks that we've been contacting via email together and finally meet a lot of people face to face. Today, the next couple of talks are going to be, as Dennis said, are going to be a little bit more about the design applications and some of the ideas that could be used to build upon what Rob and Phil have given to us so far. The first thing I'd like to show is a little amusing picture that kind of sums up some of the things that I want to talk about today, and that is how do we make the crews comfortable, and how can we learn to live and work in space? And space architecture is somewhat trying to address this with various, addressing different space environments. Also, we've come up with 3 classes of structures that we are working towards that will give us a phased approach to putting humans out into space for permanent habitation. So with that, there's a lot of definitions of architecture, and this is mostly having to do with earthly architecture. Some of these are somewhat amusing, and some of them are kind of interesting. They're mostly applicable for what we see here on Earth. In particularly, the last 2, Mies van der Rohe was an architect who really prided himself in knowing how the structure and the function worked, and so he came up with the term less is more. Robert Venturi, who was kind of bored with that and he wanted more art into it, came up with less is a bore. So we have, there's a lot of different opinions on what architecture means. However, what we're going off of is the space architecture definition, which takes off of an earthly architecture, and we define it as architectural design of living and working environments in space related to facilities, habitats, and vehicles. Designing these forms of architecture presents a particular challenge to ensure and support safety, habitability, human reliability, and crew productivity in the context of extreme and unforgiving environments. So what I'm going to do today is I'm going to take the approach of comfort zones, and this is kind of a big talk or kind of a topic that architects like to get into on how to put any kind of structure or environment for human work and living into, make the human comfort no matter what the environment is on the outside. So what you see here is there's a list of comfort zones there on the left. And some of these, Rob talked about some of these already, or as far as the temperatures that you'll see in the environments. And this is showing what the minimum and max temperature and humidity, light, sound, etc. is that is required for humans to live comfortably and work comfortably. Now, some of these are not necessarily, for instance, radiation. We still don't know the answers to that yet. Volume is still under dispute. Diurnal cycle. Can we live on a 20-hour cycle? Can we live on a 28-hour cycle? So there's a lot of things here that we don't quite know yet. but anyway, and then the charts on the right show, like for instance, this is artificial gravity comfort zone for diameter and the rate of the spin, temperature and volume. And there's a lot of other charts where we can get our figures out of. Now that I want to talk a little bit about the last one, which is resource inputs, where you have on the minimum is chaotic inputs and ordered inputs, where this is kind of the direction that we want to go with space architecture going out into space. And if you look at this chart, right now our resource input comfort zone is a highly ordered input. That's where we already have on Earth oxygen. We have a kind of a temperate climate. There's the pressure is already correct. Just here we can just walk outside, no problem. So it's highly ordered already. And what we want to do is we want to take and build in these environments down here, which you can see slightly grayed out, Earth, Moon, and then obviously there's a lot of other environments as well that we can add to that, so that we can mitigate these comfort zones such that humans could live in those environments as well. So so far the realms of space architecture include orbital environments, deep space, and also planetary surfaces such as lunar Mars and asteroid surfaces as well. And then we also include Earth extreme environments such as polar bases under the sea, emergency housing after a natural disaster or some kind of chaotic unrest. So as I go through this, we will talk a little bit about some of these environments, but we will put it in the context of how can that influence ourselves back on Earth now. Can we have some rollback of some of that technology as we go along and benefit us here as we go outward as well? So the space architecture challenge then is to try to understand the extreme environment, to work with the capacity of the transportation system, which is very difficult. And in red I have here is one of the big points that I try to get across to folks who are not involved in space industry. And that is, it's the same as requiring the building materials, the construction equipment, the power generation capability, the fuel, the air to breathe, the water, the gases, the kitchen, the food, the clothes, the medical equipment, and all the workers that are going to build the building to all fit on only one truck. So it's a very, very big challenge. It's something that we don't see on Earth because we have, if you have a bigger building, it says, well, we'll send as many trucks as we need. But that, unfortunately, the transportation system is a big bottleneck that we have to work with, and so we use a lot of devices in order to get that structure built and to be able to put the folks, the human crews on there and live comfortably in those extreme environments. So what we've come up with is we come up with a phased approach to space construction, which has 3 classes of structures. The first one is pre-integrated. The second one, class 2, is prefabricated, and then finally class 3 is ISRU derived. And this phased approach occurs over time, where you have the technology level gets higher as we go along, and also over time we're able to accommodate larger and larger crews or larger and larger numbers of inhabitants. So I'm just going to kind of go over these 3 different classes and structure the rest of my lecture around this and show some of the things that we've been addressing for ideas for building the 3 classes, and then also the actual real tests and things like that we've been doing for prototypes. The first one, Class 1 pre-integrated construction. You can see there's a couple of examples that we can see on Earth up there in the upper left-hand corner. The yacht and the motorhome. These are examples of something that's mobile. It will get you to an environment somewhere. It's already set up to live. You could, folks can just ride in them. It's the transportation vehicle as well as the end habitat. And then, of course, in space, the similar example is the lunar module, which was the descent vehicle as well as the ascent vehicle, and the crew lived there on the surface while they were there in the module, and there was no assembly required, nothing needed to be done. It was already habitable as it went. So I'm not going to spend that much time on Class 1 because we've already gone past that. The next stage that we've been working on is Class 2, and that requires a little bit of assembly. And that's where you have two or more modules or multiple parts that come together. So the example on Earth architecture, of course, is some kind of a kit of parts approach to putting your building together. And we have similar approaches that we've been using for extreme environment, such as a modular type construction system that can be continually added upon to increase the size of the outpost, et cetera, and then also inflatables and things like that. So for Class 2, I'll just go through a set of slides of some of the concepts that we've been working on. This is the concept of using plug-in accessories where you have a core pressure vessel with a variety of mobility systems, a variety of power systems, and different accessories that can plug into that. The other thing that we've been working on is commonality. You take one pressure vessel that could work for a multiplicity of functions, such as a surface rover, a low gravity rover, such as for Phobos, a hopper. You also have a space taxi or a Mars ascent vehicle cabin, et cetera, that could use the same pressure vessel, but you outfit it differently. Once you get onto the surface, the issues that we have in space for the space station, which is to put several modules together and dock them together in that zero-G environment, starts to have a little bit more difficulties because you have uneven surfaces and things like that. So in order to do that, we have to start coming up with clever ways of docking and connections, because no matter what site you choose, it's not going to be flat unless we process that site or flatten it out. And even then, there's probably a little bit of leveling and things like that that we'll have to create ways of docking those together and have a little bit of flexibility into that. Another one that we use often is deployable systems, which this shows two types. One is an actual mechanical system that has sections of the habitat unfold and deploy itself. The one in the upper right-hand corner is a EVA ramp, EVA meaning extravehicular activity. This part right here would be up against the habitat. And then while you're transporting the vehicle, it would be flat like that, but once you arrive, the whole thing unfolds to become a ramp for the crew to egress out onto the outside. And then the upper left-hand corner is a toroid inflatable habitat that is also deployable from a smaller package. Earlier, Rob mentioned the reuse, and also Phil also mentioned a little bit of that, the reuse and the repurposing of current stuff that you already have. In this case, we call this a logistics to living. In that case, we are using CTBs, which are, anybody recall what CTB, cargo transfer bags, I think, or cargo transfer bags. It's a small one-person handleable piece of cargo, and for a long mission, you would have literally hundreds and hundreds of these bags, and that's a lot of packaging material. So as you empty out each of these bags, you could take them and create partitions out of it, use it as extra shielding and things like that. So it's kind of a way to repurpose some of the material. In a similar way, there's using flexible outfitting, where if you have a set of shelving that's packed full, if it's on rails, similar to a library book shelving system, as you start to use up some of the stowage and some of the food, then you have the corridors appear, and you can move your workstation back and forth to create a workspace on this side or the other side, depending on what kind of activity you're doing. Another one is if you create all of your hard elements as where they're like a kit of parts that can be disassembled, then you come up with all of your stowage. Once that's being consumed, then you have another stack of materials. Those could be shredded and maybe melted into plastic feedstock for a 3D printer to do things all over again, whatever you want to do next. Another concept, obviously, that we would need to do for larger outposts is to be able to have a method for in-situ assembly. This particular slide shows a modular way of doing life support, where you have a core module. The core module has almost a closed life support system, and then you have multiple open systems that recharge itself off the core module as needed. This being the same core that's used in the habitats is used in a rover, and that rover then can go off and stay away from the outpost for a few days, but then it has to come back and recharge itself. And so that is bringing up the concept of an expandable outpost, where you come up with ways of putting more and more of these modules together, depending on the size of the crew, and the various life support systems and power systems are all modular that build up to support that as we go along. Now, our fourth speaker, Brian Wilcox, will be talking a little bit more about this, the robotics of it. I wanted to put this particular slide in here because one of the most important things that we must know as designers is that it's very complex. There's a lot of things that need to be included into the design, a lot of parts, and the whole key to everything is managing the complexity and putting it into a more manageable units, organizing that into modularity and organizing into things that are possible with just a few minor high-level manipulations or commands. So this particular part right here is that we need to understand the material handling of even the smallest parts. And this is especially true with robotics, because you'll see a lot of concepts out there that they say, well, we can do this and this and this, but when you get into the details, you realize that there's a lot of magic going on under there. They don't realize what the material handling is of the smallest details, and you realize that that's where the concept ends up not working very well. So then on the right-hand side, there's when we start to look at robotic construction and how habitats and how buildings and things like that can come together, there's kind of a range, or I guess on one end you have a smart constructor with dumb parts, and on the other hand you have smart parts with no constructor at all. And so with that, you can have a combination of all of those in between, and I'll talk a little bit about some examples of those. And I think probably Brian might have even more detail later on. So One, I know Brian is going to talk about Athlete a little bit later. This is one of our current NASA's methods for putting together multiple pressurized modules on a foreign planet surface, and that's using Athlete, where you have the two halves of three-limbed vehicles each are able to sandwich the payload, bring that over to a place, set that down, and then go get another module to slowly put that together. And I'm sure Brian will talk a little bit more about that in detail. So as a result, any number of modules can be assembled together without crew being present. So an example that we worked through to test some of these ideas was the lunar outpost that we did a while back under Constellation. And this is a image showing what the final configuration of that was intended to be. It had three habitable modules with multiple rovers, and we built one of the modules, and that was a mobile part of the module which had integrated into it the Athlete, and that would follow the rovers along on the surface and provide a extra supplies and things like that for the crew as they went along on the smaller rovers. It's the habitat demonstration unit that we built and tested out in the desert using a configuration of multiple modules. The bottom was a hard can cylinder with a dust module, which is actually an airlock, and a hygiene module, and then an inflatable structure on the top for the habitat. So I'll just flip through some of these. These are just examples of some of the equipment that we put on the inside. This is all example of Class 2 modular construction, putting these modules together and working out how multiple modules, even if some of them are mobile, they come together, they dock, how those would work together. Talking about comfort zones, this is some of the ways that we mitigated the extreme environment for the crew, and one is in the lower left-hand corner. This was the glove box geoscience workstation inside the habitat, and one of the issues with doing work on the lunar or Mars surface is that you're not able to just go outside and pick up a rock or whatever. There's a big, long process of pre-breathing that you have to do, because the suits are, we heard earlier, 10 psi as the typical lowest cabin pressure, but your suits can't be 10 psi, because if you are in a fabric-based suit, you would end up being spread eagle and you can't even move your arms. And so the suits have to be even lower. They have to be like maybe 4 psi or so. And so with that, then it's a serious oxygen and atmosphere mixture problem that the crews have to go through this long 6-hour process to get in the suit, go outside, pick up the rock, and whatever. So one mitigation was, in the back of this glove box are 3 airlocks for samples, and you could send out a robotic, in this case, we've got a robotic assistant that could go out and it's not autonomous. The astronaut would be on the inside controlling this as it goes, and pick up the rock, put it in the sample port, and bring it inside. So it's mitigating that extreme environment and keeping things into the comfort zone for the crew. On the top, another example is, this is kind of a 360 view of the inflatable dome on the inside, but up here this shows it all together. These are screens. And one of the ways that we mitigated a tight space is to have videos showing up on that screen, which in effect, extended the volume, the apparent volume of that habitat much larger when you have videos showing. And one test that we did, we had a person inside the habitat, and then we broadcasted live video from a vehicle from 4 directions up onto that, and this person directed the person in the vehicle to drive around and was able to immerse themselves into that environment as a way of participating in the work that was going on. Okay, so class 2. Obviously, there will be bridges that as we start to get from class 1 to class 2 and then finally to class 3, there will be little ways that we will overlap. So class 3 then is what we call in-situ construction. And that is where we're starting to, instead of taking all of the pieces and all the parts and organizing all that and going with us, which is still quite massive, especially if you have large outposts and things like that, you will want to start to use some of the material that's available, that's around you, and that's, of course, we're getting into what this workshop is going to be about. And that is, the example shown here on the right is a set of domes that are made out of sandbags, just using the sand that's on the site. So imagine if you're building this compressive structure made out of domes, and you only have a small pickup truck to carry the bags that the sand is going to go in. You can carry the bags, get out to the site, spend all your time filling the bags and build the domes without having to take all that construction material with you. Then the space example, which I'll show a little bit later, is the center hab, which is a large 3D printed habitat. So the concept is to have, for 3D additive construction, you are able to, at a very large scale, take some of the materials that Phil mentioned earlier, some of the particulates. You be careful about what the particulates are, how they will move through some kind of a conveyor system that goes to the print head, and then you either bind that or heat that in layers to make different kinds of structures. The various types of power are going to be needed. For instance, the one on the upper left-hand corner, or these two examples are using heat to do the binding, whether it's sintering, sintering as in S-I-N-T-E-R-I-N-G, or just some type of a melting or whatever. The top one is a solar concentrator. This uses hardly any energy at all, but requires a large area of lenses to focus the heat down through fiber optics to the point, and then focus that heat on the point where you're delivering this material. The other one, which would be either using some kind of a nuclear power or solar arrays, would require a tremendous amount of power in order to get the heat that you require. So for precision positioning, or some of the concepts that we looked at were the ability to have a platform that has very precision positioning of the print head, and also a way to hold the various equipment that's needed for power and also for regolith processing, etc. So from our studies, we use the athlete as a platform that is able to not only use the limbs down below, but also up high to create a very large range of you could, if you had a printer up on that arm, you could print very tall walls and things like that. So putting these together and having a modular palette that is specifically made for printing, and then using various means of material handling to get the material to the print head. So So in execution, possible applications of this, and in our workshop we'll expand beyond this and try to brainstorm a lot of ways of executing printing and additive construction processes and things like that. But in this particular example, we start off with a module that has an airlock on it and a inflatable liner stowed on the end. You set that down on the surface where it's going to be permanently, and then you go back and you pick up the additive construction pallet, and then around that airlock you begin to print vaults and domes and things like that, whatever you need to do. And then finally, when that shell is created, you inflate the liner for the atmosphere. That was some of the concept behind Sinterhab, which was done by some students a while back. Another possibility is not only printing in place, but also creating prefab panels and things like that, where you start off with a mold and then you center in place what those panels will be. And the one on the left is showing the panels being constructed into place using a series of slots that will give you a 3D structure. You could, if you had the scaffolding, you could create full arches or create an arch just as a printed piece and then tilt those up into place, like tilt up concrete. And then finally, once you have the roof in place, you can bury that with 7 meters of regolith if you want. So this one is showing just, it's an unpressurized garage that you drive the habitat in and set it down, and it has some measure of protection underneath that garage. With that then, Phil brought up a very interesting concept. He brought up the study that was done in 1980 by Freitas and Gilbreth. They're the editors of the final report of a self-replicating factory. And one of the things that space architects like to do is to take all the complex issues that are in a problem and see if they can modularize it and take that into something that will carry through all the way to the end and be applicable in every step of the way. And so I just to finish up the last part of what I had prepared, I wanted to show some work that kind of asks some of these questions and see and ask, can we take this from 4 phases. The first one is the easiest, self-constructing, then self-assembling, and then self-manufacturing, and then finally, how far can we get to self-replication? So this is the graphic where we're starting off with the big triangle on this side is showing almost everything is imported from Earth. As that goes around, the imported from Earth is still pretty big, but then you start to have in-situ participation. You're bringing in situ materials. Finally, in the self-manufacturing into things, you have maybe equal parts from both directions. And finally, under self-replication, everything is done in situ. The beauty about this is that every step of the way is going to pay off. It's going to pay off because you're reducing power, you're reducing materials and things like that you have to bring from Earth, even if it's just a little bit, and you slowly ease into it. So the exercise that we went into is, what if we came up with a module that creates a frame that's articulated on the edges with robotic means to flat pack it together. In the holes in between, you can put specialty payloads, whatever that happens to be. There's the actual version that we're working on, hardware, such that when you put these flat packs up to a structure, they unfold and they fill out a structure. So you can put this flat pack anywhere, and the modules will move themselves across the surface. And our method for doing that is the panel will connect itself to the existing structure, flip itself over, tie itself again, release here, and then continue to go. Then with that kind of self-constructing mechanism, you have a method of building structure. Then you can start to fill that in with whatever kind of functionality that you need. In this case, it's fully equation-based, and we're able to work out the kinematics. The grid of it creates a known environment rather than a chaotic environment. So you're creating your own known environment inside that you can address for all of the other functions that are coming along. So the first step then, once you get the system ready to go, is to be able to create a variety of other payloads, such as fold-out wheels for mobility, avionics, and a variety of other systems that could help fill in all the functionality that you need to do, including pressure vessels. So you can use the triangles and the squares to create a shell within which you use the inflatable liner for that pressure vessel. So just a few more. We're still in the self-assembling stage. Once we have that, then we could use this cube as a means of creating a portable factory base. And what this is showing right here is a cassette factory, where the cassette factory has dedicated payloads in each of the faces. You have a front face and a back face for material handling to get through. And so as a initial material, raw material extraction factory, so to speak, you start off at one end with the raw Regulus supply, and then at each of these cubes you have 4 payloads. And each of those payloads, the top one is material handling, tankage, and then each of the payloads is all specified for running raw regolith over to an extracted Regulus supply. So this is just one example of one factory put together for one set of processes that will eventually begin to fill out. And Phil, you probably recognize this diagram as one of the things that was in that report that you mentioned earlier. All the processes that would be needed for an entire factory that would be applicable on the surface of either the moon or Mars. So starting off with some of the 3D printer using Athlete, taking the portable cassette factory concept. This is the diagram for a batch plant for some type of a cement that could be used. You start off with the rough aggregates, supplies, various parts, and et cetera, till you get to the end to create all the processed materials that go through all the way to the end that will eventually get printed. So a further zooming in on this, these a cassette factory, one could be dedicated with for 3D printing, such as you have reels of feedstock in the back a material handling arm, and then a printer arm to create the manufactured part. Going the other way, taking the manufactured part that is maybe defective or something like that, put it into a centrifuge which spins that around, grinds it down, and you end up creating more filament feedstock again. So you have a way of going backwards and forwards with all the things that you're creating to reuse what you've done already and use it and continue the use. So you put these cassette factories in a row for whatever process that you need to do, and then this is showing we're in the self-manufacture stage over here on the right, where the factory is printing portions. You're bringing in what we call vitamin parts. Vitamin parts is a way of saying parts that are difficult to manufacture that are brought from Earth, and you plug those into what's being printed, and then finally you're able to create a stack of its own panels, and then hopefully we'll get to the point where we could just slowly add processes to slowly reach the self-replication state. We don't ever have to actually get there, just to get close. The closer you get, the better it's going to be. And that's it.